Then the next idea is when we just simulated, or not really simulated, when we calculated this dipole antenna here and found about what is the maximum charge, what is the radiation resistance, what is the voltage drop, what is the capacitance, and the area of some capacitor plates that we would need to build this, we can also try to simulate such a dipole antenna. So I will go back to the lecture slides where we have this. So this was the magnetic dipole here. We can maybe also try this one. But I think what is simpler for the beginning and easier to start with, and where we can also maybe discuss the relevance for EMC measurements and radiated emissions and so on, is to start with this electric dipole. And the software that I would like to use for this is this Concept 2 simulator that is based on the method of MoM, some numerical way to solve Maxwell's equations. It had been developed at the Technical University of Hamburg, which is now just Technical University of Hamburg, and unfortunately is discontinued. So you cannot download it from there anymore, but there are probably other ways to find it. And there always has been a demo version that can be used by students that is somehow limited in the complexity of the models that you can simulate, but for these, let's say, hello world examples it's totally enough. So I've already opened up this demo version, and I think there's nothing here, so it looks like a blank project. And so in this simulator, we would now like to simulate our dipole antenna here, and we will just use, as it's shown in the lecture slides, we will just use a single wire. So no top loads, just a single wire and a source in the center. Okay, so here on the left side, you find all the stuff that you can do there. And yeah, if we want to have a wire, we probably need to go to wires. And there you can see, okay, you can load wires. You can also import something from a computer-aided design program, and we would like to have a new wire file. So I will give this a name, call this dipole wire. And then next step that we can choose here is a certain number of base functions per wavelength. And 8 seems to be the default setting here. If we increase this, it gets computational more, there's more computational effort. But okay, we just have this one wire, so we can probably go up to 10, 20, something like this. So, or maybe we will leave it at 8 and look later on what changes or what happens if we change this. And yeah, then we need to have coordinates for our wire here. If we check the coordinate system here, yeah, the wire is pointing in Z direction. The X coordinate and the Y coordinates are both 0, right? And so if I want to have a wire of 1 meter length that is oriented like this, what would I need to set here as values for the starting point? 0, 0, and then half of the length in the minus direction, once again 0, 0, and half of the length in the positive direction. Okay, then we need to select the radius. We have not cared about radius of our wire yet. Or what would be a lucky guess, maybe? One millimeter, maybe. Okay. Okay, and so here we have number of base function. I think if we insert nothing, it will just use the value there. But okay, maybe let's set it to 8. Okay, and apply. And okay, and then we get a wire. And so you can zoom in and out with the mouse bar. You can also see how the coordinate system rotates. I'm not okay. And with if you press the control key on the keyboard, I think you can somehow pan and move it around. Right? Okay, so this is our wire. So we now have a wire, this wire here. What do we need to generate some current or to excite this? We need to have a source somewhere. And sources we find here as excitation. And now we can say, okay, we can have a voltage generator. And the voltage generator is placed on a certain wire. So we have just one wire. So we say it's on wire number 1. It's in the middle segment. It has 1 volt of amplitude and 0 degree phase shift. We could now, of course, set the voltage amplitude to what we calculated here in our exercise task for the voltage, 8.77 millivolt. But maybe we just leave it also like this as the 1 volt. Okay, so I will say apply, then you see, okay, there we get the voltage source at the center and say okay. And now we have a wire, we have the source. What else do we probably need to set to have the same thing or more or less the same thing as in our exercise task here? We need to set frequency, exactly. So in frequency, we can set here at frequencies, and then we can say we want to have a single frequency, for example, and go to 1 megahertz. Okay, and then I think we have set everything we can run. So we run this concept simulation, and then you can see it does something here. Yeah, so I'm using version 12 from 2019, just with one thread for this certain frequency. It computes a matrix. This just takes less than a second, does some decomposition to solve this matrix, and the total time for the simulation is less than 1 second. But of course, it's also a very simple problem. Okay, so this was here the simulation view. Then we can go to post-processing. And there are different ways to look at the result. So we can look at current and charge distribution, but I think this is current charge distribution on surfaces. We don't have a surface here. We just have current distribution. We just have a wire. So we could look at the current distribution on wires. Hopefully this works, because something should happen now in this window, but this program is calling GNU-plot in the background to do the plotting, and sometimes they are, let's say, not properly connected with each other. Okay, so we say we want to have it on our dipole wire. On wire number 1, there is just one wire for this particular frequency, and maybe we don't want to have real and imaginary part, we want to have the magnitude. And maybe let's do it without any interpolation. So if I click OK, hopefully there's now a plot appearing. What would you expect what we should see in a plot? If we have a horizontal axis that shows us the position along the wire, and for each position along this wire we look at the current magnitude. What should we see? We should see something that we had seen in the table here before. Oops, this is was too much. Yeah, we should see something like this. That we have maximum current in the center where our load is, where our source is, and 0 at the ends because we don't have any load. Okay, so let's try it out. And luckily it works. Yeah, and so we get a triangular current distribution, which perfectly makes sense. Okay, so maybe if this view works, let's do not fiddle too much around with it. But so yeah, what we could see is now that the current that we have in the center, the maximum current, is much less. It's something also in the microampere range. And even if we have now 1 volt of excitation and not our 8.77 millivolts, so the amplitude here does not really work, unfortunately, because we don't have this top load, and the current distribution does not fit to the assumption of the constant current thing. So, but what might be interesting to discuss is if I go back to simulation and if I increase the frequency, maybe go from 1 megahertz to 10 megahertz. What would you expect? I will rerun the simulation. Okay. Now it gets even smaller because I think something is already preloaded in the background. If I go back to this post-processing, do the same thing once again, what would you expect? Before we had 300 megahertz of wavelengths, now I've 10 times the frequency. So what happens to the wavelengths? It decreases by a factor of 10. So instead of 300 meters that we had before, that we calculated here, now we have 30 meters. But 30 meters in comparison with the 1 meter is still long. Or our dipole is still short in comparison with the wavelengths. So nothing should change. And nothing changes. Now this is unfortunately really an imaginary part that is plotted here, but because I think this did not save this setting, but okay, for the magnitude it's still looking the same. Okay, so let's increase the frequency once again by a factor of 10. Let's go to 100 megahertz. So at 100 megahertz wavelengths is 3 meter, and so now our dipole is 1/3 of the wavelengths long. So if I plot, something interesting happens. It does not look super triangular anymore. It somehow gets rounded. And so now if we find this case, this one here, where the length of the dipole is exactly half of the wavelengths. So if our dipole is 1 meter in length, then this would mean our wavelength should be 2 meters. Because 2 divided by 2 is 1. So now the question is, at which frequency we have 2 meters of wavelengths? So here we should get 2. And the question is, what do we need as a frequency? Or we can also say the frequency, of course, from this equation is c divided by lambda if lambda is 2 meter. What do we get for the frequency? Three divided by 2 is 1.5. And 1.5 times 10 to the power of 8 is 150 megahertz. So if we set 150 megahertz for the frequency, we should get this current distribution here, a half wavelength dipole. So let's check. We go to frequencies, we go to single excitation, we set it to 150 megahertz, rerun the simulation once again, go to post-processing, do this thing here with the magnitude. And okay, and then we see, okay, we get this nice half wavelength dipole current distribution that is also printed there in the table. And now we see, okay, if this function is now round, we see that it gets some, let's say, edges here and there, because these are the limits that we have due to our number of base functions that we selected. And so I think I could solve this problem if I choose some interpolation here. Maybe let's choose this maximum value of 7, whatever this means. Yeah, and then you see, okay, it gets more rounded, but this is some kind of interpolation. So if we delete this interpolation once again, go back to plot magnitude, okay, there it's rough again. And so now if we go back to our wire file, edit this wire file and say instead of just 8 base functions, I would maybe like to have 20 and apply and run the simulation once again. Go back to post-processing, show this without any interpolation, the magnitude. Yeah, so then this is also getting rounder here. And we see, okay, it's getting some dip here in the center because something still happens at our source that is connected there. Okay, so now let's go back to frequency. And yeah, what would you expect if we double the frequency? If we double the frequency, what happens to the wavelengths? We have half of the wavelengths, and so now we have at 300 megahertz, what is the wavelength? It's 1 meter. So our dipole antenna has the same length as the wavelengths. So we have a full wave dipole, and we can set this, simulate, go to post-processing, look at this current distribution, and then it looks like this. And then it looks rather edgy once again, but this is also what we would expect for a full wave dipole, that the current in the center gets small once again, but that you have like half of the wavelengths on one side, half of the wavelengths on the other side. And so, yeah, we now would need to have a bit more base functions, maybe go to 100, to have this in a nice view, simulate, go to post-processing, show it once again. Okay, yeah, and then it looks like this. And this is something that, yeah, if you have lots of time and if you are familiar with solving Maxwell's equations and so on, this is something that you could somehow still calculate, not by hand, but let's say by writing down some code in MATLAB, solving using method of moments for an equation that describes this dipole antenna. But of course, it's much more convenient to do it here in such simulator. Okay, so if we go to higher frequencies, even more, if we would go to, let's say, another 150 megahertz more, if we go to 450 megahertz, if I resimulate, what would you expect? What happens? Frequency gets higher, wavelengths get smaller. We have more wavelengths along the dipole antenna, so we get more ups and downs. Okay. So, yeah, and this would now happen if we would go to higher and higher and higher frequencies. But imagine, I mean, it's not a super high frequency. We have something now that has 1 meter in size and that radiates at the frequency of 450 megahertz, and 450 megahertz is not a lot today, let's say. We're talking about gigahertz of frequencies and sometimes even terahertz of frequencies. Okay, so I will go back to our initial frequency of 1 megahertz, simulate once again, go to post-processing, and we can check what else do we have here. We also have 3D radiation diagrams. So let's have a look at this. And so, yeah, you can choose how many CPUs you would like to use for this, and you could have electric far field and electric near field. We will stick to the far field. You can choose the scale, and you can choose how many steps. Yeah, here, how many steps, what is the range that you would like to have in theta and phi, so in spherical coordinates, and how many steps you would like to have. And this is somehow set to 60 for theta, so this is the theta angle. So we get 60 different steps for this, and this is the phi direction. This is this one around, if I'm the dipole, so 30 steps for this. And before I click OK, what would you expect? How does the radiation pattern of a dipole look like? What does Homer Simpson likes to eat all the day? A donut. And we see a donut. And so the radiation pattern of a dipole looks like this. So the wire would be in the center. Remember, the wire is pointing in the z direction. So this wire is radiating a lot to the sides. And it's not radiating anything to the top and to the bottom. And yeah, so that's why it looks like a dipole. And so now if our wire would be not an antenna that we have built to radiate on purpose, but it would be some equipment under test that we test for electromagnetic emission and interference. If it would be some unintentional radiator, and if we would like to find the maximum emission of this radiator, it would be fairly simple because however you rotate this dipole, from which side ever you look onto this, if you would measure, let's say, 6 directions, yeah, 4 from the side, 1 from the top, 1 from the bottom, you would always find the maximum direction. No problem to do so. Okay, so we can check what happens if we go to higher frequencies. So once again, if we go to 10 megahertz, wavelengths there was 30 meter. Remember, the dipole was still small in comparison with the wavelengths. So what would you expect? No changes. Should look like before, and it does look like before. Okay, so then let's increase factor by frequency by another factor of 10. So now wavelength was 3 meters. Dipole is a third of the wavelengths. Okay, and it's still looking like a donut. Maybe the donut is a little more flat, maybe a little more compressed. It's not yet that obvious here. So if we go to 150 megahertz, our half wavelength dipole frequency, if I simulate once again, go to post-processing and plot, yeah, so then it still looks like a donut. This was, remember, when the current distribution looked like this one here. It's still looking like a donut, but the donut is more compressed. So if we go to the 300 megahertz frequency, there we had the full wave dipole. There our current distribution looked like this one here. So let's check the radiation pattern once again. It's still looking like a donut, but now you can see it's really compressed together. Yeah? So it's more, it has a higher directivity radiating to the sides. So before, what we had before was more like a light bulb radiating in all directions. Now it's more like a flashlight that it's somehow compressing the radiation to the sides. And you can also see this in this nice table here, that our short dipole had 1.5 of directivity. So in the main beam direction, it's radiating 1.5 times more than on average. And so for the half wavelength dipole, this increased to 1.64, not really noticeable. But for this full wave dipole, we already have 2.41 something. Yeah, so the directivity increases. And now you can imagine if you go higher in frequency, the directivity, or one lucky guess would be if we go higher in frequency, this directivity increases. So one lucky guess would be that the dipole gets flatter and flatter and flatter. But if we go to this 450 that we had before, yeah, where you had the multiple things going up and down along the wire, if I resimulate, what happens is that looks like this. Yeah, so now you have like many, remember, if we looked at the current distribution looked like this one, many ups and downs. So it's a little bit like if you have many small dipoles along the long dipole, and all of them radiate and they interact with each other, or each of them creates its own field, but they are somehow superimposed with each other. So there can be positive interference and negative interference, and that's why you get something that looks like this. So yeah, there is some very compressed donut in the center, but they are in this case two much larger loops that are somehow radiating towards the top and towards the bottom. There's of course still nothing that is radiating towards the top, and there will never be. Yeah, so if we go higher in frequency, let's go to 600 and resimulate and go to post-processing, and then yeah, then we have now just these two. Then it looks like a, I don't know, diabolo, maybe something like this. Now it's not radiating anything to the side, not radiating anything to the top and to the bottom, but just to something in between. Yeah, and so now if we go to, I don't know, 1000, let's go to 1 gigahertz, 1000 megahertz, and simulate and go to post-processing, and yeah, so it stays within this pattern. And so now maybe our resolution here in theta is a little coarse. Maybe I would need to increase this to also maybe 100 or 120, and then it gets a bit more smooth, but then it also consumes more computational power to rotate this on my computer. Okay. Questions, ideas so far, comments? So we can shortly check what else we could do here. So there is some 2D radiation diagram. Okay, I think the 3D one is more easier to understand. So this is electromagnetic fields in arbitrary planes. This is not interesting for us. Power flow through surfaces. Frequency domain system responses. Here we could calculate, for example, the input impedance or some kind of radiation resistance. Time domain response, okay, it's not interesting. Yeah, input impedance in the Smith diagram. This is maybe what you can check out later. Network parameters, line integrals of electric and magnetic field, radar, cross section scattering results is this, and generate equivalent current. So I think just maybe these two or these three are interesting for us. The next thing that I would like to change, so if I rotate this and if we look at this from the top, then of course everything always looks like a circle. Why does it look like a circle? Because of symmetry, because it's just one wire. If I look on the wire from the top, why should there something depend on the angle around the wire? So what we could do now is to make this model, let's say, more, if we think about electromagnetic compatibility and if we think about radiation testing or radiated emission testing, then typically our equipment under test will be much more complex. There will be not one straight wire that radiates, but yeah, if you look at the wires here on my desk, they have strange patterns. So we can edit this wire file and we can append one more wire and connect this, for example, at the bottom of our dipole and let it point into the x direction. So if we add something that maybe points 0.3 meter into the x direction and at the bottom of this dipole 1 millimeter radius and maybe 30 base functions and say apply, then we get one more wire. And this wire should of course break up our symmetry. So if I resimulate, if I go to post-processing, take a look at the results. Yeah, so now this radiation pattern gets more strangely shaped, more complex. It's not round anymore, and yeah, it's something that we had before, but for example, now it radiates much more here to this bottom than to the top. And now if you would have the task to find the maximum radiation of this, and you don't know how this pattern looks like, right? You don't know how, you only know how the structure looks like. Okay, you could have a lucky guess that maybe because there is more wire at the bottom, it will radiate more to the bottom, but no one really knows. And so here now the problem is, if you go to some anechoic chamber or semi-anechoic chamber, to find the maximum emission, you need to do very fine steps with the turntable to find this maximum here. And this problem increases if we, yeah, so we could add another wire at the top. So let me edit the wire file, add another wire, say at the top, which is at 0.5, I will add something that points in the y direction, maybe 40 centimeters in the y direction, at the same height, with the same radius, and maybe 40 base functions, and apply. And so now we have two wires. Now it looks like this. Let's resimulate. It still goes very fast. Go to the post-processing. Yeah, and now it's somehow radiating more to the top, more to the bottom. Always takes some time until I can fluently rotate it, yeah, and not so much to the sides. And so if, remember, frequency is still not super high, just 1 gigahertz, maybe if we go to 2.4, which would be Wi-Fi or Bluetooth. So if we go for higher frequencies, smaller wavelengths, something is wrong now. I think I forgot to set here giga. So there's the radiation pattern. Yeah, and so now this is this gets very small and narrow lobes, and probably my display here is not sufficient enough. Probably I would need to have more steps for the theta and phi direction, but then it's too much computational effort for my computer to do it. Yeah, so but the radiation pattern gets very small and very narrow lobes, and it really takes time to do this small, narrow turntable steps in the semi-anechoic chamber to find the maximum emission. So in this case, for large equipment under test, for high frequencies, for small wavelengths, for electrically large radiators that are larger than the wavelengths, or even a couple of the wavelengths, it would be much better to go into the reverberation chamber or mode stereo chamber and measure total radiated power there, because there, however complex this radiation pattern is, it will radiate. The radiation or the wave will hit the wall, will be reflected, will be reflected, will be reflected, and at some time it will be picked up by the receiving antenna, and you can measure the emission in terms of not of maximum field strength in a certain distance, but total radiated power, which is a much more robust measurement for this emission, let's say. Okay, I mean, the good thing is, and by my small frequency selection mistake, I've more or less already spoiled the answer. So yeah, so now we could add more complexity. We could add another wire and so on, and make this more complex, and then this radiation pattern would get also more complex. Let's say the good thing that saved us in EMC the last decades is, however complex your structure is, if you once again go down in frequency, so if we go back to the 1 megahertz or even 10 megahertz that we had before. Maybe even it works with 100 megahertz still. Yeah, so if this structure is smaller than the wavelength, so now here it is again just a third of the wavelengths. And if you simulate and look at the results, it still once again looks like a donut. Yeah, you can see that the donut is not, at some positions it's a bit out of shape, yeah, because of this unsymmetry of the model, but it's still a donut. And this is what saved us, let's say, many years and many decades in EMC, that we had fairly large equipment under test where we would measure the emission, but the frequencies were so small that everything radiated more or less like a dipole. And as I said, it's very simple to find the maximum emission of this dipole. But if we go higher in frequencies, yeah, we can check again the 1000 megahertz, then things are already getting complicated. Yeah, and so then you get these strange radiation patterns, and then at some time it just does not make sense anymore to continue with the old-fashioned way of measuring radiated emissions in a semi-anechoic chamber. It would be much more practical and feasible to measure total radiated power in a reverberation chamber. Okay, what further questions do you have? What else shall we try out? I mean, as said, you can try it out yourself. I will upload the concept software to this Moodle course, so you can just download it, and hopefully this student demo version then still works. But it works on my computer. I think the student license is not restricted there. So maybe what we can try out, I don't know if it works or not. Let's maybe go back to the original frequency that we had at 1 megahertz or of 1 megahertz and simulate. And so now our radiation pattern, yeah, exactly, is just the one of a dipole. So now if we check this Smith chart function, oh, I don't think that this is useful, but here we have some input impedance of our generator. Yeah, so this makes sense, but we have just one frequency, so there is just at this one frequency we have one point. So this does not make too much sense, but what we can try, and for this I will delete, where can I delete? Append, delete, from wire 2 to 3. So the last small thing that we can maybe try out, we have the dipole antenna from before. It's 1 meter long, pointing in a z direction from minus 0.5 to 0.5 meter. And before we always just set a single frequency, but now we can maybe set a range of frequency, a frequency loop for a special interval. So let's say we start with 1 megahertz and we end up with 1000 megahertz, and we will do 1000 frequency steps. So we have 1000 frequencies in steps of 1 megahertz, and generate a value list. And there we go. There are our 1000 frequencies. And I will click OK. And there's, of course, still the voltage source, the generator in the center. So now if we run the simulation, then we have, of course, 1000 frequency steps. So we need to wait some time. Each step takes some milliseconds. And maybe I can already, while the simulation still runs, go to post-processing. And what would be interesting to look at now after we had looked at radiation pattern and current distribution, is to look at the input impedance, the impedance that the source sees from the dipole. And so simulation is finished. Now we can take a look at input impedance at our generator, at the voltage generator that we have, and say apply. And okay, and then we get a curve. Oops, then we get a curve that looks like this, that at low frequencies the input impedance is very, very high, because we just have this one wire. At zero frequency, it's like an open circuit with infinite input impedance. And so at 1 megahertz, it's still some almost 60 kilo ohms, something like this. And then the impedance goes down and obviously reaches some minimum at around 150 megahertz. So why at 150 megahertz? And maybe I can, while you think about this, maybe I can try to, but obviously we cannot. I would like to scale this axis in a logarithmic way, but obviously it's just linear, so you cannot see the minimum here very sharply, but there is obviously a minimum at around 150 megahertz. So at 150 megahertz, the wavelength is 2 meter, and the dipole length was 1 meter, so we have this half wavelength dipole. And there, the input impedance or the dipole is well matched. This is when we had this current distribution. So here input impedance gets small, and you can also see that the radiation resistance also has a certain value here, some kind of fixed value. Okay, and so then if we go up in frequency, we get another maximum. This is at around, shortly before 300 megahertz, and then it goes down again at 450 something. And so these are these frequencies that we also checked before. And it would be probably nicer if we'll be able to scale this in a logarithmic way, the amplitude axis. Okay, but this is just a short simulation example how the input impedance of this dipole antenna, of the single wire, changes over frequency. And of course you also see here the frequency points where the antenna is short in comparison with the wavelengths, when the antenna is half of the wavelengths, and when the antenna is full wavelengths long.